I think it's absolutely awesome that you decided to come on, uh, especially because a lot of I know this from experience. We always feel like everybody is so much more skilled than experienced, and it's intimidating, and we don't want to hand in that call for paper or whatever because we feel like we are not good enough or something. And so I think it's amazing that you had the confidence to and also to want to help out with this charity stream by the Blind Hacker. So I think that's awesome. I think you're doing great.
Here, exactly. Like, I, I,
Yeah, I couldn't agree more.
it's fantastic. I will say this, and I want everybody listening, watching live, watching it on repeat. Click this section, whatever you need to do, share this out. You have value. I want to hear what you have to say. So does anybody else here. Live Overflow, Slice Hosting, myself. Where yes, we might be out there. We might be popular streamers. At least those other two guys are. But it's you have a voice. I want to hear it. They want to hear it. Somebody wants to hear what you have to say. Please say it, regardless of whether this is the Pride stream. If you want to start your own stream, you know, I want to hear it. Just say it, please. Please say it.
And I missed. How old are you? Are you in high school or?
16. 16
Yeah.
years
So
old.
I mean, I started when I was 19, 18, and everywhere I've went, I've been the youngest at every place. So I think it's really just about trying to learn and trying to get to that next step. And don't feel like pressured or there's always going to be someone that knows more than you. That's just life, right? So I think to just try to find a skill that you're good at is really the best way to go. And that's why I'm like, hey, there's other places that you can go in IT, not just pen testing. But I think to just understand all of it is good if you do want to go down that route. So I couldn't agree more with what everyone's saying.
Yeah, there's like this thing in the community. I'm gonna be very quick about this. There's this thing in the community that's like the imposter syndrome thing.
Yep.
It's unfortunately very contagious, and I was actually kind of slightly affected by this. And like, it's some sort of behavior that I actually kind of inherited by seeing other people basically do this thing. But then at the same time, it's like vain. It's like a very vain thing to do. There's no point in doing so, and yeah, the reason why I was actually like talking about like Android reversing it though this isn't there's a certain set of people that I actually appreciate because they actually work on this topic and they've actually managed to make some very great discoveries such as the Leadscape and Zane Wong. They do some pretty amazing stuff with Android reversing and something that I've actually slightly experimented with, but like I don't think that it would be actually fair for me to actually not only to other people but especially to myself. Like I don't think that would be actually fair to portray myself as somebody
Oh,
that doesn't represent me. That's something that I've actually had to do for years. That's something that I'm actually trying to get over, especially because yeah, I used to be kind of afraid of expressing my opinion on certain stuff, including of like telling other people, yo, this isn't okay or whatever. Like I'm a gay person. It's and like I have no idea how to put this. Oh my gosh, the time is up. But yeah, I'm gonna like to sum up. I've kind of tried to be more open about the way I think, about the way I feel. But yeah,
and
this is something that
that's why we're here, man. We want to support you, and that's why I'm glad you came out here as both a infosec rookie, as a gay person. I have nothing but respect for you, dude.
Okay, I think I'm gonna go ahead and drop off. I got some errands to run, but I'll be back in probably an hour to watch the rest of the stream.
Appreciate it, and Livid, you can stay and hang out and get to chat with your idol Live Overflow here, man, and he's up on the screen, and we're ready. Again, dude, I think you did great. Your personal interview was fantastic, and love it, dude. I want you to grow and be in this industry. I want you to grow as a person and express how you need to.
You know, I want to jump in and say thanks too. I actually had your stream going and my kids sitting here listening to it, so you were already becoming a role model for the next generation.
Holy fuck, I'm so flattered right now, like seriously. But yeah, I don't think it would be fair for me to actually take up more time. So yeah, I'll just like, how to put this in the right way? I'll just stop talking. Yeah, this didn't sound right. This definitely.
You're doing great, man. You're doing great.
Holy fuck, you guys are so supportive. Jesus Christ.
All right. We are live with Live Overflow.
Yeah, hello everybody. Can you quickly confirm that the audio and the video setup is going fine? How is
It looks like on my end. Can somebody else confirm? Because again, my laptop died. I had to go grab a charger.
Yeah,
It looks good to me, yeah.
All right, okay, that's perfect. All right, welcome. Thanks for having me on. I thought for this stream today, we talk a little bit about the basics of electronics. And I have to mention that I am a complete amateur in this. I come mostly from the software area. And so for me, electronics is just a way to understand more, I don't know, how technology works. And so I've only done electronics as part of being an amateur, and I thought I'd share my amateur views on it and try to explain it to you, hopefully from like one amateur to somebody who is maybe a little bit less experienced yet. So I try to, I hope I can explain some concepts that I thought were kind of like mind-blowing or mind-opening the first time I encountered electronics, and so I kind of want to share that with everybody who has basically zero experience. So I try to get you from zero to something, I guess, so that you have maybe somewhat of an intuition or an understanding of the basics of this kind of electronics, digital electronics, I guess. Yes, and so I thought to do this, I start to show you here. I've brought two boards. Let me see. Let's switch to this camera here. So I brought here a Raspberry Pi and an Arduino, right? And so when I used to look at these are representative basically to any kind of PCB that you might find in whatever devices. There are a lot of components on it, and it looks rather complicated, and it looks crazy, right? These kind of PCBs I've looked at as a child and didn't understand a thing, and so it makes me quite happy as an adult to now look at these and kind of somewhat understand it. Now, these devices are already pretty modern. They mainly have like a few black mysterious chips on there, but on older devices you might find still a couple of other chips. On here, the Raspberry Pi and the Arduino, both of these chips are basically full computers inside of these black packages. And the stuff around this is kind of just to make that computer work. So these chips have already an incredible complexity inside. So I think it's better to take a step back and maybe go like, what is it, like the 60s or 70s, to look at much more simpler black chips, but they, I hope, give you a better kind of intuition for what is up with these mysterious black chips.
Well, you do know why that they were not really labeled back then as well, right? This is I'll say this is speculation.
Okay, all right, speculate.
I've been explained to that the reason that they've been unlabeled is during the quote Silicon Valley Wars and stuff. People didn't, when you'd go crack into your PC, they didn't want you stealing or being able to look up part numbers easily, because they wanted because those chips had value. Like you could literally pull out parts and sell them, make thousands of dollars potentially.
Oh wow, that's interesting.
I don't know if that's entirely true, but that's something I heard from one of the people that I learned from in my early days.
If you hear a weird whining in the background, then I'm sorry, that's my dog. Maybe he shows up at some point and says hi too. Yeah, so I mean, that sounds reasonable to me. I mean, nowadays we still get sometimes devices where the chip's numbers on it are removed for, I guess, security reasons, especially some kind of high security chips that you can imagine in some kind of payment terminal. They might not be labeled, or they might just be custom. They might not really have a label on it. but nowadays, I guess this this kind of competitiveness has kind of faded away, luckily. So nowadays we actually have chips and they have something on it. So if we look at this chip now, if we get the lighting right, you might read on there a certain number, and you can search this number and you will find parts, spec sheets and stuff like this for this. So now, I thought we start with a very basic chip. Now this chip I have here is part of the 74 series. 74LS32 is its number. You can see that on there. And so I wanted to show you here quickly Wikipedia, because this is something that one of these, and it's pretty basic and boring, but for me that was some of these things that I found fascinating. If you look at this is a whole Wikipedia page about this series of 74 chips, and they have been used in mini and mainframe computers of the 1960s and 70s. So if you were that old and you might have opened up a computer back then literally your computer might have been built with these kind of chips. And I find this extremely fascinating. Now, what does this mean to have this kind of series? It's kind of like a standardization, and this series is defined which number is what kind of functionality. And when you go further down in this Wikipedia article, you might, it's not here, list 7400 list. There are list of 74 series integrated circuits. So you can see that each number just defines what is in it. So the 7400 would be, for example, a quad 2 input NAND gate, and a 7402 might be a quad input NOR gate. So these are fairly basic chips. If you know a little bit about like binary logic, then NAND and NOR, AND gates, or inverters here are very basic components. But they do get a little bit more complex and have a little bit more stuff in it, but we just keep it a bit simple. There are just a few more gates basically in the other ones. And so I want to specifically look right now at the 7432, and that is labeled as a quad 2 input OR gate. And so what we can do is we can basically look up that part number 74LS32, and we can find the datasheet of that chip and see what it means to have this kind of chip. So first of all, on the image to the right, you can see just the chip outlined, and basically, it's this orientation of the chip with its pins. And so at the top right, for example, you have VCC, that is the your power supply, your plus 5 volt, and GND is ground. So that's the other side of that. Now you get the circuit. And then the other pins are inputs and outputs. And so you have A and B as the inputs and Y as the outputs. If we look here a bit further down, we also find a logic diagram for this. And so maybe you have seen this maybe in university, school, or somewhere else. This is an OR gate, and it shows you that there's an input A going in, an input B going in, and there's an output Y. You see the how you would write that in in that kind of formula. Maybe you also know that from school. And so this is the chip form of that gate. You even get here the true internals. Like, it is a bit complicated. You see here transistors and a lot of resistors, but this thing tells you exactly what is inside of this chip. Like I said, inside of these chips are a lot of small gates, and maybe you have seen these kind of like chip microscope pictures. And there's a website called Silicon Zoo, which is kind of a bit dedicated more to reverse engineering chips by opening them up, for example, with certain chemicals, and then going in there with various tools like microscopes to look at these layers of silicon and copper inside of these chips. And so, for example, here is like that's not shown here. So this is, for example, how an inverter would look like. This website is great if you want to see that exactly explained, what you can read out of it. It explains it very well, how you can basically look at a picture of it and then reverse engineer what kind of gate it is and how it works. It's called Silicon Zoo. Check it out. So, right. So now we know how this chip is connected. We have A and B as input and Y as an output. And so I would say let's just play around with this. Basically, this I have done on the past week on stream. We are building something that I will introduce just in a couple of minutes. But let's start basic. Because when you want to get started with electronics, you want to physically play around with it and build something. And so what we have here is a breadboard. It's used for prototyping. And basically, it's just very convenient to build something and prototype something. You have on the sides, you have basically your power rails. All these holes on the side are connected with each other as a line, and you can also see here a plus and a minus on it here in the corner. So this is the plus and the minus line. You have that on both sides, and then in the middle there are always these pins. These 5 holes are always connected, so they are always connected like this in rows. And so you can build with this. So what we can do is we can take here the chip that we got, the LS32. It's hard to see with the light reflection. And you can see that that it has like a notch on the top side. So this indicates the top of the chip. And so we can put that just as we want on there, and we just have to remember that this with the notch is the top. So let's just put it somewhere here in the middle. Okay. I try to answer questions in the middle, especially when we are building now, because that might be a little bit more boring. So if you have some questions, I try to incorporate that somehow. Okay, so now we want to play with this, and so we need somehow to connect inputs to this chip. And so I have these buttons here. So these are regular buttons that you have maybe seen on various devices. They just have a button here at the top, and they have these connections. Now, how exactly do they work? I have here a multimeter, which we can use to kind of show how such a button, kind of like what you can expect when you connect this. So this multimeter is on a setting, no, not yet. Now it's on a setting that it will beep when it detects that something is electrically connected. So now it doesn't do anything, and when we touch the metal tips, then you hear it beeping. That means as soon as it beeps, you know it's connected. Pretty clear. If you have a wire and you touch both sides, it beeps. Okay, so when you hold this now onto this button, well, they are very tiny. You don't hear anything. I hold them now at both feet. But when we touch it, when we press it, then it beeps. Okay, so this means the wires are the paths are disconnected, and when you press it, you connect it. So that's important to know. And so let's plug in 2 of these somewhere. Now I need to remember, I guess, the length where I had planned this. So let me see. So this would maybe go in here, for example. So we could put that here. And the other one could go here. Oh, and now I bent the legs. This is always the problem with this electronic stuff. How long have I been working on the 8-bit computer? So yeah, we will get to the 8-bit computer just in a couple of minutes. But yeah, I've been working on it basically for now like 13 days or so maybe. All right, okay, so we have these buttons now, and now we want to connect these buttons to the chip. So I have here prepared this wire so we can connect to the one input. And remember, if we look at our schematic, we can see that the top left is the A1 input. And so we are connecting here A1, the top left. So like I mentioned, the notch indicates the orientation of the chip. So you can see here that we connected the top left pin, the first pin, A1 to the button. And we do this now with the second button as well. Getting a bit crowded here, but this doesn't matter. I need to put this one over. There we go. Okay, so both these wires are now connected to one of the pins of the button. And so what we now basically have to do, we have to now create a circuit. Which means, first of all, oh, we forgot, we need also obviously to connect our chip to the power supply. So we need VCC at the top right, that is the 14th pin. We have to connect that to the plus, to our power rail. Come on. There we go. And then in the bottom left, we have GND, that's ground, which has to go to the negative rail. And then also these two sides are not connected with each other. So I've prepared here these cables to just connect these two sides also together. All right. Next, we can add some LEDs. So here I have some colorful LEDs that we can connect to the buttons because we want to kind of see when we press these buttons. So what we can do is, so we defined by the yellow cables that this is the output of the button. So as you remember, when we measured here the two legs of the button, we know that the left and the right leg are not connected. Only when we press the button, they get connected. Okay, so left will be the input and right is the output, which means we can connect our LED to the right side of the pin. So one of the pins of the LED is plus and minus. The short one is always going to ground. So I will decide that we have the power connection like plus 5 volt coming into the pin, into the button. So when you press it, the plus 5 volt would flow through here, would flow into the positive side of the LED, and then out of the negative side, of the ground side. And now we need to connect that to ground. And because it's like an LED, we want to make this LED only takes needs 2.5 volt, but we will work here with like 5 volt. So we need a resistor to make sure that the current is limited. Yeah, you can, these values of these resistor, I would say, are not important right now. You can calculate them based on the specs. There are plenty of tutorials. I just want to get this faster done. Okay, and so we can also connect the second one. Again, the yellow is the output, which means we have to can put that in there. Uh-oh. Uh-oh. Did you hear that sound? My PC is complaining. Okay. So now they are connected. Now let's try this. Okay, so theoretically the LEDs should now be connected to so that it lights up when we press the button. So we can connect the power supply here. I have over here like a power supply. It's this thing here, and we can turn it on. Okay, nothing goes up in flames yet. Checking. Okay.
We hope ever.
Okay, so obviously I'm dumb because obviously it can't work because we forgot to connect the buttons with power. Okay, so let's connect the buttons here. So the first one connected. Okay, it's connected, and the second one. Let's do that too. And now let's quickly review what we built there. Oops. That is obviously connected to the wrong input. I have kind of reversed those buttons here, but whatever. Okay. So now we can press both buttons and the LED turned on. So now let's quickly check. Power is coming in from the red wire here, goes all the way through here, comes, for example, to this bridge, goes over there, follows here through, and goes onto the left side of this button. And so now there's no connection. It's open. But when we press it, the circuit is closed, and it can flow onto the other pin, flows out of here, flows into the one side of the LED, flows through to the other side, and then goes into this resistor, back to ground, travels then back to ground, and goes out of the black cable. That's kind of like how the electricity is flowing. And at the same time, we have now connected also the yellow over to the chip. So this will serve as one of the inputs into this OR chip that we just looked at. Okay, however, we have a problem now. So the problem is, now let me switch here also the multimeter again for measurement. So this is now, we measure now the voltage. So we can measure now, we can go with our black tip to the ground, and with the red tip we go to the 5 volt, and we will measure the 5 volt input voltage. So that's great. However, if we now measure the output of the button, we will measure like weird stuff. What, 1.4 volt? What is that? The output of the button? That's weird. If we press it, however, now let me press it at the same time. It's a little bit tricky. Okay. So we press it. Now we read 5 volt. If we don't press it, we read something weird like 1.5 volt. That's really weird. And this is bad because it serves as input for our chip. And if you think about it, actually right now there's absolutely no connection, right? Like this is just an open wire. This button only connects when we press it, but it's not connected to the circuit at all when it's disconnected. And this is what's called like a floating state. There's no input and weird stuff happens. Where this 1.5 volt current comes from, I have no clue. Ask somebody who has studied this. But this is kind of weird. So what we want to do is we want to make something that when the button is pressed, then the 5 volt are flowing, and when it's not pressed, everything is properly still connected to the circuit but to ground. And you can do that with a so-called pull down resistor. This is a resistor that will pull down when the button is not pressed to ground. And that is very simple. We have here a very high resistance resistor here that we just connect now the output of the button to the ground rail. We connect both of these outputs to the ground rail. So now, right now, you would basically think we have a short circuit if you think about it. Am I thinking about that? Yeah. No, we don't have a short circuit. No, wait. We don't have a short circuit right now. Now, okay. So right now, the input of the chip, if you follow, so to say, where the input is coming from, follow your yellow line over there. You come over here to the button, where the button's coming out, but then you can follow it through the resistor back to the ground rail. So now the input of the chip is connected to ground. That seems great. However, if you now press the button and you connect those wires, then it seems kind of weird because you have plus 5 volt flowing in through the red thing, going through the button, you press it, it's connected, and then it flows directly into ground, and that's quite literally the definition of a short circuit. So when you press it, you would, if this resistor weren't there and was just a connection, you would have a short circuit. But thanks to this resistor, it's not a short circuit. This resistor value is chosen in a certain way to prevent basically a short circuit. The resistance is high enough that no short circuit is caused. And that's called a pull-down resistor. Now, if we press it, it still works fine. But if we now measure again the output of the button, what we should see is that we now see basically 0 volt. It's really flaky. Minus 1 volt, I guess we take that too. It's, no, was it minus? Okay, I have no clue.
Some people are suggesting that there might be an issue with the power. Are you providing?
We were talking about a issue with a laptop.
Oh, it's a laptop.
Yeah.
Okay, just kidding. You're doing great, dude.
Okay. Yeah, no. Okay, so basically here shines my amateurish through. I have no clue why I measure this. But what is clear is now that this now the problem is like when we are connecting and measuring, like maybe we introduced something into this floating cable when it was open. Like it maybe changes stuff. I don't know. But what is clear now the input is connected to ground through the resistor, or when we press the button is connected to 5 volt. That's kind of the important thing. Maybe we should measure it over here. I wonder if that makes a difference. No clue. Okay, whatever. That's just one of these things actually that I've also wondered on stream, what exactly are pull down and pull up resistors. I kind of know where to place them, but I just like barely understand it. But people have been very helpful, have been writing me. I thought I explained it now fairly correctly, but I guess there's still something I don't understand. But that's all about, right? I'm an amateur. I want to learn as well. Anyway, so now we have the inputs here. And so theoretically, now we can connect to the output. And the output is the third pin here, Y, and we can connect that over here. And so now that should be the output, and we can take another LED. We connected this. The LED flows into this one leg here, goes out the other leg, and now the other leg, again, we connect with the resistor to ground, just to make sure. Okay. Clearly, I connected something wrong. So now we have to do live debugging. Oh, god damn it. Let me see. Okay, so
Have
maybe
you
this...
tried filling the buffer with some A's?
Try filling the buffer. Okay, so now chat, you have to help me. Okay, so we have... It's a correct chip. It's a 32. That's, I guess, important. So VCC is connected. Ground. So the problem I have is this is supposed to be an OR chip, right? Or is it an... Yeah, it's an OR chip. Which means it should be dark when there's no input and should light up when there is power. And so it should only glow when we press one of these buttons. So that's the fail. So let's see. Okay, the power is correctly connected to the chip. And so then we can look. The first input is here, the second input here, and the third output is here. The output is generally corrected correctly. Output goes into the LED through the resistor to ground. That also seems fine. Now, the buttons are connected on, let's go with the first button, are connected, goes in here, has no other connection there, that's fine. And so on the other side, the output is then connected to this chip. And then we have, so the pull down resistor is going to ground here, and the other side of the LED is going to ground here. So that looks fine. And then we have here VCC coming in. Okay, I have absolutely no clue. This looks absolutely correct. So, what we do now? Okay. Oh no. Oh, wait, what? Wait 1 second.
Uh-oh. Small interruption. Well, it's a good time again. This is the 2019 Blind Hacker Charity Pride stream. So remember, guys, donating to me is great. I will donate all the proceeds of today to the charity directly. At least if you donate directly to the @donate link or through Twitch itself with bits, you're around later on when we go to do a raffle drawing. We are giving away that beautiful fossil watch that is what's the word, pictured online. So feel free to donate, stick around for that. Will be a good day. It's not the one that I'm wearing, by the way. I bought I was gonna actually give one to the highest bidder and then one randomly, but I really kind of liked the watch so much, I'm keeping the second one. What is going on? Uh-oh. Is that live overflow troubleshooting power? It sounds like. Yeah. Yes, there's a watch being given away. So if you hang out through the whole stream and you're in the chat, by the time I go to do the drawing and you've donated and I'll pull out I've got a bot select to pick people, and if pick person and it says that you've donated, you'll win. I will ship it to you at my cost. Ads. No, it's not an ad. Live Overflow had a slight issue. It'll be right back. Hey, thanks for the follow, everybody. Thank you so much. I'm gonna. He's tied up the. Let's see. Can I figure out who followed me from Twitch itself? I am at a loss at the moment. Oh, Poochie. So how are the other hosts doing today? Thank you guys so much for hanging out.
Pretty good.
Still good.
Fine.
Still good.
Online.
Yeah. Guys having fun so far? Since this actually seems to be doing a lot better than I thought it was going to go. Oh, gee, Purple Fox heard me throwing out lots of curse words trying to troubleshoot the early stuff. I was losing it. Things were being thrown.
I never did ask how'd you figure it out? How'd you get it with Discord like that?
Fucking magic. I don't know, dude.
Turned it off and on again.
I rebooted. Well, at the seriously, it was supposed to start at noon. That's why I had to reboot my system. I rebooted the computer. I rebooted the system. I rebooted all the equipment attached, the microphones, the stream. I don't know what started working, but finally I said, screw it. I'm just going to host my entire screen, which is why I can't do some stuff in the background. Maybe if I go to do this again, I will find a better way. Maybe we'll find some lighter weight software than Discord. So maybe I'll find out if I can just set up I think people have talked about like Apache with XAMPP, some multicast stuff. So we'll cast to that, and I'll capture. I'll set up a VPS and OBS and show everybody. Have instructions on how to stream their screens to that. There's plenty of options because honestly, I've got a good board here and people listening on the Twitch. I've honestly thought, if this was going to be successful, if this is successful, so far it is very successful. I'm very proud of it. But I wonder what people would think about a online conference instead of going to DerbyCon, instead of going to ShmooCon, instead of going to DEF CON. If I can line up talent and people who will present on their slides and stream like that, could I do 3 days or 2 days a weekend of 8 hours of people a day? Like, what do people think about that?
That would be interesting.
I think we've seen All Day DevOps have a great showing in the community because of that. So I think there's already a precedence for it.
Excellent. Yeah, no, that's kind of what I thought. I've seen, I know video game streamers, they do 24-hour charity streams or, 48 hours. They stay up the whole weekend and, demolish themselves. So I'm thinking, if I can put the call for papers out there and get people to do it, we'll create a Twitch just for that, and we'll call it, Twitch CyberCon or something, and get all that stood up. And if there's an interest of it, we can do it.
Whoa, what was that? Sorry for I don't know who that was. Actually, in my chat, somebody solved the flag, but I think it wasn't posted in your chat. So here's the flag again. I posted in the TheBlindHacker chat. And there you go. Yeah, thanks so much for participating. I thought it was a small interacting stream. I guess people were a bit too lazy to type off the base64. Okay, so literally I have no damn clue what the mistake is. I built this before, and before it worked. Oh, buddy, are you okay? No clue. Okay, so here you can see live that I'm also constantly failing. I literally have no clue what the problem is. So,
is it a bad board, you think?
I don't know. I don't know if
you bent a pen earlier. Is that potentially stopping the passive electricity?
Yeah, I don't know. I wonder if if just one connection is kind of dodgy or whatever. But I'm curious. I mean, it was hopefully visible on stream. Maybe I can look later at it, or somebody will write me, you were so stupid, you connected it completely wrong. So I'm looking forward to that. If you are that person, I wait for your Twitter DM. But I guess I got the point across, hopefully, that these things have gates inside and you can somehow hook them up, okay? It's maybe a bit more complicated than I wanted it to look like. It's maybe you make a bit more mistakes than it's maybe not that easy as I'm hoping it to show you, but you can clearly see that, oh buddy, but it's yeah, well, whatever. So what I want to show is black chip has some gates inside. You can look up the data sheets, you can see what's inside of them, and theoretically, if you are maybe not a noob or follow some other kind of examples and don't watch my stream, then maybe you will also be able to connect 2 buttons to this chip. Anyway, so what I wanted to go from here is now, and what I was kind of hopefully wanting to, I mean, what I kind of show you now is when if I connect it directly without the buttons, it's kind of working. So let me show you here. So both of the inputs are right now connected to ground, and if I connect, I believe the input defaults to high here, so maybe I should have done a pull down resistor instead of pull up, but I'm not so sure. So the default is high, and if I change one of the inputs now, this LED turns on. And if I put that both to 0, then the output is off. That's an OR gate, right? It has, the output will show if one of these inputs is high, and only it's off when both are off. So it's a simple gate. And so I kind of understood this at some point. I understood, okay, wait, there are these gates, there are these logic gates and an ORs. But how the heck can you make out of something that seems so static, where like just electricity flows into one side and it comes out on the other side and decides it based on some logic gates? How can this do something? How can this execute something? Where are the different states? How does the clock play into all of this? How can you make a computer out of something that seems so static? And so the next kind of like mind-blowing thing, I want Ben Eder to introduce this. So this is the video series that I've been following the past week, and this part is where he explains something called an SR latch. And as you can see here on the screen, Ben Eder has done something very weird. He has connected the output of the OR gate back into the input. That seems odd. Why would you do this? But this kind of hacker mindset is what you, I guess, need to make more out of something that seems so static. So let's quickly listen into that.
Input to a 1 by pushing the button. So if we push the button, the input's a 1, so a 1 and a 0. We get a 1 as the output, and we see the output comes on. But actually, this output is now coming back into this input, so B is a 1 as well now. So actually, we're pushing the button, so we've got a 1 coming in A.
You can't hear
it. We've got a 1 in B, and so the output is still 1.
Okay, right, I forgot. Okay, the problem with the setup with this code right now that you can't hear the output of the OBS, you can only hear the microphone. Okay, wait, so then I just try to explain it, what Ben Eder is explaining right now, unfortunately with a less soothing and less nice voice. So basically, as you can see here on the screen, he has connected the output of the OR gate back to one of the inputs. And based on the truth table, if no button is pressed, the output is 0, right? So the output is 0, goes back 0, 0, A and B is 0, everything is fine. But the crazy thing happens is when you press, you can hear the video? Oh. The video's audio. Oh. Okay. I'm sorry. Oh, never mind. Sorry, I'm torn between 2 different streams right now. On my stream, you can hear it on the Blind Hacker charity stream. It's not coming through. So I'm explaining. Sorry. I got confused. Okay. But when you press now the button, right, the A, you turn the A high, you can see that on the truth table on the right, B is still 0 because the output was 0 from before. Then suddenly the output becomes 1. And now this output goes back into this OR gate and has here now a 1. And now when you release the button, suddenly it stays like this, right? There's always now a 1 on B because B is on and A can be whatever, it's an OR gate. The output will always be 1. Suddenly you have latched the output. It was off, and as soon as you press the button, suddenly you latched a 1 in there, and it can never be undone again. This OR gate will always have a 1. And so connecting back the output back into one of these chips creates, it's like one of this hacker creativity that you need, because it feels so wrong to have this connection suddenly going back into the input. But these are the kind of building blocks that you can use to create much more complicated setups. And also I'm skipping a little bit forward here in the video to minute 9. So because here he has now connected 2 NOR gates in a little bit more complicated setup. This is now the SR latch basically. As you can see here at the top, you can see 2 NOR gates. They have 2 inputs, and you can also see this on his breadboard right like above me there on the breadboard. There are 2 buttons and 2 LEDs. The 2 LEDs are the output and the 2 buttons are the input. And you can see that these NOR gates are somehow weirdly connected back to the input. And what basically now happens is, you can play this through yourself. It's kind of fun. He has drawn it here. He explains it in the video. I won't waste too much of it. I just show you, let it play here at some point.
We've swapped.
He will just press the buttons in a moment. Okay, so if you press this one button, nothing happens. And if he presses the other button, now, come on, the output flips over. Now the other set is set. And so with these buttons, he can now switch between the different states. And you have to appreciate this ingenuity that this output is now latched on, it stays on. It's not a static thing. There's a feedback loop going back in, and it keeps that LED on. And when you keep pressing the button, nothing happens. But now when you press the other button, then you change the state of the circuit. It flips around, the other LED stays on. You can keep pressing this button, nothing happens. Right? I need to switch back to TheBlindHacker. On these headphones, TheBlindHacker and the Discord is. So these kind of building blocks introduce a state in what seemed previously just something where electricity flows through one side coming out on the other side, thanks to these feedback loops. And so Ben Eder has this whole series on explaining and building an 8-bit computer. And part of the series, he explains these kind of concepts. And there are now multiple videos. You can see them in the playlist there about the SR latch, the D latch, and then finally the D flip-flop. And so it's kind of increasing in a little bit of complexity, but Ben Eder explains this very well. It's a video series I can highly recommend, and I'm learning a lot from it as well. So, as I said, Ben Eder is building here an 8-bit computer on breadboards. You can also find this on his website, eder.net. And here you can basically see the final product. He is using these old chips that have been used in mainframes in the 60s and 70s and basically builds his own 8-bit computer with it on breadboards. This design that he's using is actually coming out of a very old computer electronics books. And it's kind of, the architecture is kind of called SAP, simple as possible. So it's very minimal. In one way how it's minimal is, for example, that it only has 16 bytes of RAM. 16 bytes of RAMs. You can only put there 16 characters in there. And in that RAM, you have the instructions as well as any memory that you might need. So the most complicated program he was able to write is like Fibonacci. And so it's quite amazing that he got that into 16 bytes. But if we now look here, this is basically what we have building on stream the past few days. And so this is how far I have come. Oh, we have come on stream. So here you can see a couple of different modules that we have finished. And so I just plugged it in and turned it on. And now you can see the LEDs coming on. And at the top here, this is the clock module. And the blue LED blinking here, that is the clock of this computer. We are using here again a Mysterical black chip. It's called the NE555 or 555. It's a very famous chip, and it looks very simple from the inside. Ben Eder explains very, very well how this chip works, but this chip can be used to generate a clock signal. And we have also here a variable resistor, because the resistor is kind of configuring this chip. And that's another lesson I've learned about this kind of hardware that kind of blew my mind coming from the software world, because these chips all look so static, but you can actually configure these chips as well based on other components. And so, for example, the 555 chip can be configured based on capacitors. They can like load up, hold a charge, and release the charge, and that stuff can take time. And through that charging and decharging time, you can, now that makes kind of sense, like with the clock, right? It charges up and releases, charges up, releases. You got kind of a clock. And also through different resistors that control how fast these capacitors are charging or discharging. And so that's how you can configure this chip. And so that's like a function or whatever in software where you have a config flag that controls something, and in hardware it's these resistors and capacitors. And I find this super fascinating.
Oh yeah.
Yeah, and so you can see it blinking here now, and you can also see it do stuff on the right side of the board. Right now, these two modules that you can see with these 2 rows of LEDs are the registers. So right now we have 2 registers, and in between we have the ALU. This is the arithmetic logic unit, and what it can do is only addition and subtraction. Now, what is happening right now is that both these chips put their value into the arithmetic logic unit and basically perform an addition. So this register value plus this register value, and then the control circuit is set up right now that the output of the result of this addition is put onto the bus, and in between here in the middle is the bus, and these LEDs here in the middle that you can see are representing the value on the bus. So the result of this addition is placed into this register. And now I'm slowing down a bit so that you can really see this. With each clock cycle, with each lighting up, with each rising edge of that clock, the B register is currently configured that it reads in the value from the bus. And this is done through these flip-flops, these registers. These registers are built based on flip-flops. And so with each clock cycle, it just reads in that value. And remember that register outputs its value to the ALU, where it performs an addition with the other register. That register always keeps pushing out its value, and with the next edge, the new result is then loaded into the register. It's placed into the addition. Like this addition happens instantaneously. Like the rising edge comes, the value is loaded in there. There's a new value. They just continuously just output. Like these things are just directly connected. Immediately the result will be on the bus, but with the next edge, the new value is read into the register. Immediately the new result is there, but with the next edge, this new result is back read into this register. So this keeps right now currently performing an addition. In fact, it's actually basically doing a subtraction, because we have here all the LEDs on 1, 1, 1, so that's basically like -1 in binary. Whatever, Beneder explains that very well. It's the 2's complement of the number 1, so it's like -1, whatever. So this is how far we've got over here. This will be the RAM. We are currently building this here. This, as I said, has 16 bytes of RAM. 16 bytes are can be addressed by 4 bits. So this dip switch can allow us to select the memory address in RAM, and down here we are building right now the values. Not that important, we are not finished here yet, but later this is how we will program this computer. We select which address we want to write the value to, and then we select the value, and then we write that into that RAM address, and then we go to the next byte and write the next value in there. And that's how you can program then this computer. It's kind of crazy. Another thing I wanted to show you while we are still having some minutes. And I have here a setup with a smartphone, and it just takes a moment. Please don't let us down now, because this thing is just such a garbage product. It just takes a moment. All right, so now we can hopefully switch to this screen. Awesome. So on the screen right now, you can see a FLIR camera. So that is a thermal camera, and it shows you the temperature of the setup here. You can see my hand, it's like lighting up yellow. Now, you see these chips lighting up, and it looks kind of dangerous. Oh my God, they are getting really hot. But if you look at the temperature scale, right now my room just goes like, in the bottom right, you see the lowest value it sees is like 25, and the highest value is 35. So yes, these kind of white, yellow-looking chips get warm. They get like 35 degrees. It's a bit warmer than outside, and they are just barely warm to the touch. But the thermal camera really exposes this. So here you can see electricity and physics just coming together and heating up these chips, because there's like current flowing through these chips, and the thermal camera really shows you this and what part are lighting up. Now what's also interesting, if you can kind of see this, like here it's oddly bright, right? Right here at these connections. And these are not chips, these are just literally the wires that are coming in from the power supply and then distributing the power. And this again is just physics. These wires here, these metal, I show you here on the other camera, they are just like little pointy wires that are plugged into the breadboard. And so they just have like a touchy connection. They are just touching the other metal. And so it creates a very small area where these wires are electrically connected. There's a lot of air in between, so the resistance is quite high. And so all the current this is currently drawing like 0.8 ampere, this whole thing. I can see that on my power supply right there. It says 0.83. So all this power, all this electricity has to go through these very tiny points, and so that causes the material to heat up in those places. Not a lot, like it doesn't feel warm at all. You know this is like not that hot at all based on this temperature scaler, but still the thermal camera reveals here like this physical property that when electricity flows through these cables, and so for example later we might want to replace with properly soldered cable, so that it's not just kind of like touchy the metal, but they are soldered together, and then the connection is less resistive and causes less temperature. At least that's my amateur understanding. Disclaimer again, I'm just an amateur. I try to explain it in my words how I understand it. This might not be entirely correct what I'm saying. Okay, so there's one last thing kind of I want to mention. So what kind of architecture is this? We have talked about this on my stream a little bit, what kind of computer architecture this is. But it's kind of like our own made-up architecture. However, you might have heard about these classifications of Harvard architecture or von Neumann architecture. And you can kind of look at what their definitions are, and you can kind of classify things with that. And it somewhat makes sense that we have these definitions, so we can kind of wonder about how would we define or classify this build here. Now, I mentioned this has only 16 bytes, so we could imagine an addition that we maybe are separating the code from the data. We could have two different RAMs. One is the RAM data, and one is the what am I saying? One RAM data. One RAM has the code, and one RAM is only for memory. Now, memory and code would be separated. That is an addition that we could build. And some of you might have heard about Harvard versus von Neumann architecture and kind of remembered that Harvard architecture, it would be a Harvard architecture when code is separated from data. And von Neumann architecture is when the code and data is intermixed in one memory. But here's a cool ARM article by ARM about this, and so we can kind of learn a bit more about this, because not only is it about if code and data is separated, but also how they are connected to kind of the main computer here. Because in our case we have a shared bus, so even if we would separate code and data, we have a bus where all the things are connected together. And in the original Harvard architecture idea, each memory segment also has its own bus, its own connection to the main unit. Anyway, let's read a couple of sentences from this ARM article here. Harvard architecture has separate data and instruction buses, allowing transfers to be performed simultaneously on both buses. Von Neumann architecture has only one bus, which is used for both data transfers and instruction fetches. Therefore, data transfers and instruction fetches must be scheduled one after another. It's possible to have two separate memory systems for a Harvard architecture. Now, the problem is in modern systems, for example, your computer, you know that we mix these things together, right? The data and code. When you look into a Linux binary, or you run a Linux binary, you look in memory, you can find in that memory the data as well as the code that it's executing. If you have ever done buffer overflows and with shellcode on the stack, you know that you can like write instructions into the data on the stack and jump there and suddenly it's getting executed. So these things are intermixed. However, they are only mixed on that level of abstraction. If you look at it actually in more reality, then you can actually find that modern machines are actually using both. So they are caches inside of the CPU that are separated from each other. And these caches themselves are basically memory cells that are acting like Harvard architecture, while the real RAM, the actual RAM that is connected to, is then actually more von Neumann architecture. So long story short, the point is, and that's kind of what I wanted to end my part here today, is that especially in tech, we often have definitions and they feel always so rigid and well defined, and this is how it must be, and we learn this in school. You got to learn the checklist of what is Harvard and what is von Neumann. But in reality, in the physical world, and when we look at what we are actually building, is that these are just made up classifications that are just made up by us, and they maybe make sense in some situations to use these terms because they have a certain meaning, but in many cases, something that we are building in real life might actually be both at the same time, might be one thing on that layer, might be the other thing on the other layer, and we have a mix of both, and these definitions are not strongly defined, and they are not strongly meant to be that way, and we are not forced to make a Harvard architecture with two separate RAMs that use two separate buses. We can also make our computer to have separate memory for data and instructions, but use a shared bus and mix these things together. It's all great. It doesn't matter what, so to say, the definition that somebody has made up needs to be. So basically, wink, wink. I hope that kind of came across what I would try to say there. Yeah, so that's the end of basically my segment. We have a couple of minutes. Maybe BlindHacker, you have some questions. Maybe Chat has some questions, and then we can.
Yeah, does the charity stream chat have any questions over here? Does the any of the hosts also still here have any questions? I think it's gnarly, dude. I've been watching you build this. As you see, I'll pop in and I let it run in the background since you usually stream about 3 p.m. My time, and that's kind of late in my workday for me. It's just it's really cool to have seen this come together from one board to two boards to three boards to what do you got now? 7 boards?
Yeah, we are working on a 7th one. Yeah.
I think it's fantastic. Like this is super hobby nerd stuff that you're learning it, you're rocking and rolling. I really like it, man. I can't wait to see till you actually get some code passing through with some instructions and code, and it's going to be super neato, man.
Yeah, I just wanted also to mention, maybe some people are wondering, why are you wasting your time with this? But there are multiple reasons that I think it's very valuable. First of all, I like anything technology. I want to learn more about electronics, and I think that's a cool project to learn more about electronics. And I also have somewhat of an understanding how a CPU works, but also not really. For example, how the actual instructions will later be executed is something that I still have no clue about, and I'm so looking forward to get to this execution part to really understand how later all these different modules are working together to suddenly execute programs. This is also something I have no clue about, and that's why I was motivated to do the stream. And I strongly believe by understanding better and better the technology, by venturing out, and even if it's not like, that's not directly my job related, I don't do anything in my job with electronics, but I do get a better sense of understanding of everything, and I feel like it also helps me just be better at my job in security by having just more ideas from different fields and seeing this ingenuity and the hacking mindset that has gone into building these kind of things. They really always inspire me, and I feel like it also makes my work better.
Absolutely. Cool stuff, man. You guys can check him out on YouTube, Live Overflow. You can check him out on Twitch, Live Overflow. You can check him out on Twitter, Live Overflow. And he's. Are you going to continue building this after this today, or are you going to just wait till the weekday?
No, so this weekend right now is the Google Capture the Flag competition running. So after this, so this was my stream basically for today. I will go right back playing CTF, and I will probably maybe go to live tomorrow. I try to have it a daily thing. I don't have a real schedule.
Love it, dude. Thank you so much for stopping by, man.
Yeah, thanks to you so much for having me. I wish everybody for the great stream. Thanks for setting this all up, and yeah, I'm glad I was be able to be part of this.
I'm glad you were here too, my friend. See you around.
Yeah, see you.
Yep.
Thank you.
All right. Let's see. Let's get it. All right. Let's see.
Okay. So that was the stream. Oh man. I can't believe that I failed building that OR gate. Holy hell, how bad and embarrassing this was. God damn it. But yeah, okay, so this, I really hope somebody, I couldn't pay attention to chat. I read now the backlog. I really hope somebody was yelling at this screen and trying to tell me what is wrong with it, because I have no clue what I screwed up at that OR gate. So yeah. So how much does it cost? Oh, that was the other chat. Might not hear it anymore. Oh, host the blind hacker. That's a good idea. Oh my gosh, I would have probably forgotten this. Oh, god damn it. Thanks. All right. Okay, yeah. Like I said, I have to go back to the Google CTF right now. So far, if you want to look at the challenges I have looked at, so we can kind of like look at write-ups together when the CTF is over. I'm looking basically at the web challenges right now. This is the BNV challenge and the paste static challenge. These two I've invested quite some time so far. I haven't solved them so far, so if you want to look at the challenges I looked at together, I guess you can do that. Can you make some high quality picture? We can debug it on Twitter. That's a good idea. I will try to extract that image from the stream because I ruined my setup. I tried to debug it. But yeah, good idea. All right. So thanks again for hanging out. Thanks for being part of this. I will host now the Blind Hacker, and see you then the next days to continue building this here. Yeah. Bye bye. Hosting now.